In the last lecture, we built our first meaningful computation, starting from a truth table through building sub-expressions, expressions, and eventually applying a circuit for one-bit compare for equality. So we asked if we have two one-bit numbers, A and B, can we build a circuit that tells me if they're equal? They're both 0 or they're both 1. Okay, incredibly simple, maybe not very useful. So let's see a few more examples of this, and the next example is going to be a 4-bit compare for equality. So what do I mean by that? So remember that when we specify binary numbers, we specify how many bits and whether they're signed or unsigned. So for now, let's just do unsigned 4-bit binary numbers. I have two 4-bit binary numbers, and I want to return true, 1, if those two numbers are the same, and 0 otherwise. Okay? So let's just start turning the crank. So the first thing, and this is really where all the hard work is figuring out what is the truth table. What does the truth table look like? How many input columns? What is the output? And then populating that truth table. So let's, of course, start there. Well, okay, so first of all, what does a 4-bit binary number look like? So here it is. Let me label them A0, A1, A2, A3. This, of course, is the most significant. This is the least significant. So that's my first binary number, 4 bits. Let's call that A. But notice that there's actually 4 numbers there. And then, of course, I have B, which has B3, B2, B1, B0. And I want to know, are these two equal? Well, what does it mean for those two numbers to be equal? Well, it means that A3 is equal to B3, A2 is equal to B2, and so on and so forth. Okay, so notice that even though I only have 2 numbers, they're each represented in terms of 4 bits. So I actually have 8 input columns, right? A3 to A0, B3 to B0. So don't get confused by numbers and bits. Because we are living in binary world, we have to always think about the underlying bit representations. Okay, so I have, let's see, 4 here, 4 here, that's my input, and I of course have one output, which is C. It's 1 when they're equal and 0 everywhere else. Okay, if I have 8 input, how many rows do I have? Remember the relationship? 2 to the power, the number of input. So in this case, it's 2 to the power 8, which of course is 256. That's a lot of rows you have to populate. So you have to go through every single of the 256 possible inputs, write out a row, tell me what the output value is. And you could do that. It'd be a little tedious, but you can do it. But let's think about whether we really need to go to all this trouble or not. Because when we think about it in this 2-bit, in this 2 4-bit numbers, there's really, I'm sort of doing a very simple computation over and over again. So what is that? Well, I sort of said it. I said that this 4-bit number A and this 4-bit number B are equal if A3 is equal to B3 and A2 is equal to B2 and A1 is equal to B1 and A0 is equal to B0. So really, if I could solve this 1-bit problem and then this 1-bit problem and this 1-bit problem and this 1-bit problem, well then I could just logically combine them using an AND operator. So maybe we can simplify this calculation a little bit and not have to populate that full 256 row table. So let me remind you what the 1-bit compare for equality looks like. I take 2 single bits, so careful with the switch in notation here. You can think of this as A0 and B0, and this is telling me whether those 2 bits are equal. So these are just 2 1 bits. And remember that the way this circuit works is it says if they're both 1, so if they're both 1, then this AND will respond 1. If they are both 0, they go into NOT gates, they flips to 1s here, this will respond to 1. So if this is a 1 or this is a 1, then I get a 1 out here, otherwise I get a 0. So this is the 1-bit compare for equality that we did before. Let me draw this with a little bit of abstraction, because this is a lot. I don't want to have to keep drawing this over and over again. So I'm going to represent the 1-bit compare for equality with this little box here with a 1 CE, 1-bit compare for equality. And done. Now there's two levels of abstraction, right? Because here there's two transistors, here there are two transistors, but I don't draw that every single time. I just draw this little abstraction for what a gate looks like in terms of transistors. And now I can draw another abstraction for the entire circuitry, and underneath it is this, and underneath that is a bunch of transistors. So again, that power of abstraction. And now let's think about how do we combine those little 1-bit compare for equalities to get a 4-bit compare for equality. Well, again, I want to compare A3 and B3, and I want to compare A2 and B2, and so on and so forth. And of course, I still only have a single output, which is if these are equal, and these are equal, and these are equal, and these are equal, then I want to say yes. Otherwise, I want to say no. All right, so let's start pushing the bits through the compare for equality. So A3 and B3 go through a 1-bit compare for equality, and out comes what? A 1 or a 0. If it's 1 if those two are 0, 0 or 1, 1, and it's a 0 otherwise. And similarly, I can push A2 and B2, A1 and B1, and A0, B0. So each of the bit positions, each through their own 1-bit compare for equality. Notice the power of the abstraction here. I don't have to write an entire circuitry. I can just write that little box, and I know what it is from the previous slide. Now, what do I want to do? So I have 4 outputs here. And what do I want to do? Well, let's think about what the rule is. The rule is that this should be a 1, the output to the entire circuit, if this is a 1 and this is a 1 and this is a 1 and this is a 1. I know how to do ands. I just need an and gate now. So this should be pretty easy. Notice, by the way, the and gates only take 2 inputs. So I can't shove all 4 of those into an and gate. So I have to do them 2 at a time. And it doesn't matter what the order is, of course. So these 2 go into an and gate, and now this will tell me if they're both 1. And then I'll take the output of that and I'll shove it into the AND gate, an AND gate where it's the bit down here, and then I'll do that one more time. So let's just think through the logic here. Let's say that let's say they're all 1s, just to make it simple. So out of here will come a 1 because they're equal. A 1 goes into the AND gate. Out of here will come a 1. It'll go into here. So this is a 1 coming out. The first 2 bits are equal. This is a 1 coming out here because they're equal. Out of here comes a 1. This will go into here. This will be a 1 here, and eventually 1. And notice if any one of these are not equal. So let's say these are not equal. Well, then a 0 comes into this AND gate. And that means a 0 comes out of here. And if a 0 comes out of here, a 0 comes out of here, and a 0 comes out of here. So once one of these AND gates flips, any of them, because one of the bits is not 0, we get 0 on the output. And the only way we get a 1 on the output here is if these are equal, and these are equal, and these are equal, and these are equal. And so now look at the power of this circuitry. I've got a really simple circuitry here, here, and here. I've got 3 AND gates. So instead of having to build a truth table of 256 entries, build all those sub-expressions, build the expression, then draw a fairly complex circuitry with 8 inputs and 1 output, with the power of a little bit of abstraction, I was able to do something a little bit nicer. So I use this example because one of the things we'll be talking about is, yes, we'll want to turn that crank on the circuitry, truth tables, sub-expressions, expressions, but sometimes it's really inconvenient. Sometimes we have to be just a little bit more clever. Okay, so that's it for now. When we come back, we're going to design a couple more circuits, and we're going to keep sort of seeing how these things are built and how to build more and more meaningful computation. So I'll see you in a few minutes.